to 1. I'd like to give a little time for Shikha to catch a breath. She just came up here. I'd like to call upon Veda, Prakash Galigekere from Oak Ridge National Lab.
So hi everyone, thanks Girish. So my name is Veda and I'm from Oak Ridge National Lab in Tennessee, USA. And I'll be presenting on high power wireless charging system development. I'll try to focus less on the technology itself, and as I talk about the projects we're working on wireless charging, I'll try to bring out some of the technology challenges and something which is relevant to the flavor of this conference. So Oak Ridge National Lab is in Tennessee, and it was started right after World War II, and it was actually started as a part of the Manhattan Project, and it was in the middle of nowhere then, and that's kind of the reason why it was started in the middle of nowhere, because they wanted space which was away from the public eye. And recently you might have heard of Summit, which is currently the fastest supercomputer in the world, which was deployed there last year. And 7 or 8 years ago, the most recent element which is added to the periodic table, Tennessee, was also kind of discovered there. So I work at the Power Electronics and Electric Machinery Group at Oak Ridge National Lab, and we deal with all aspects of electrified transportation. And when I say electrified transportation, we are more into the research, R&D, and the technology to improve the power density, make the inverters smaller, make the motors lighter, and the core enabling power electronics of the systems. So we are very well vertically integrated. We don't make the semiconductors ourselves, but we get the bare dies from different manufacturers. We do the packaging there, and from there on, we do the packaging, the device level protections, the inverters. We use a lot of 3D printing as well. We recently did a 50% 3D printed inverter, really high power density, liquid cooled, air cooled inverters. And we're also working on motors to get away from some of the critical materials which are geopolitically sensitive. So we're developing motors which do not need those kind of materials. And so as power electronics being the base of many of the applications, we take these technologies to transportation, the grid and the transportation interaction, which is a very important thing, and renewable energy integration as well. So Department of Energy sets targets, which is very ambitious. So if you take the kilowatt per liter of the power electronics on vehicles, on-road status is around 18 kilowatts per liter. The 2015 DOE target was 12 kilowatts per liter. But the target that the DOE has given us is 100 kilowatts per liter for 2025. So that's kind of the push which is required to make the systems lighter, cheaper, more dense, and make the whole system sustainable. So why electrified transportation? This theme has been touched upon many, many times in this conference. But in the US, 30% of the energy is consumed for transportation. And 30% of the greenhouse gas emissions is also from transportation, not surprisingly. And I don't know the exact number for this number for India, but I'm expecting this to be going up quite exponentially because of the urbanization of the population and the income going up. The transportation sector is growing a lot, so the pollution is going up as well. And one of the big questions we get is electric vehicles are expensive, right? I mean, that's a very simplistic way of looking at things, because right now the battery cost, upfront cost might be more. But if you look at the entire cycle of using an electric vehicle, charging it, and then the motor is very inexpensive and there's no combustion, so the mechanism of propulsion itself is a lot simpler. So in US, it's the cost to maintain and run an electric vehicle is half the cost of keeping and running a gasoline vehicle. So I don't know the numbers if what's the cost of petroleum here and what's the cost, I don't know the comparison, but I'm thinking it'll have similar benefits because oil is more expensive here. And where is the big push for electrified transportation coming in from? One of the big sectors is fleets, like UPS, the FedEx, the Ubers, and those people see a lot of benefit economically. And like it was said before, Uber plans to go all electric in London by 2025. And we have an interesting project with UPS where we are doing bidirectional wireless charging for them. So we'll be wirelessly charging the UPS truck at 20 kilowatts, and the UPS truck is capable of sending 6.6 kilowatts back to the grid when it's not charging. Why do they do this? Because you take a UPS facility, they might have 100 or 150 trucks, right? And if each of those have 100 kilowatt hour battery storage, when there's a power outage, you have a big energy storage there. I think Tesla started a 100 megawatt lithium-ion energy storage system in Australia, which is the biggest in the world. If you have 1,000 UPS trucks, you equal that. So there's a lot of other things which go on other than the economic and the societal benefit. So what are the challenges? The main challenges are charging. That's the first thing we ask. How long does it take to charge? And once I charge it, how far can you go, right? So the solution is you have to charge it quickly, so you need fast charging, or the other solution is you charge often, right? So you either charge often, you charge quickly, or you charge on the go. That's the dynamic wireless charging. And that's still in really R&D kind of phase, and we have a project going on that as well. Maybe down the line in future conferences I can talk about dynamic charging, but I'll stick to stationary wireless charging now. So why wireless charging? Because it's convenient, and the transportation sector is going to be autonomous. It's going towards autonomous because of the 5G and the Internet of Things and all the other things which are coming in. And if your car is autonomous, the charging has to be autonomous. I mean, it kind of doesn't make sense if the car is becoming autonomous, but you have to plug it in. And with the requirement for faster charging coming in, as the power level goes up, your cables get bigger and heavier. And if the cable is 20 feet long, it's going to be like way more, and you'll have to start liquid cooling it. That's going to add sophistication. So wireless charging kind of makes sense with all these situations. And here are two pictures where there's one stationary charging where there's a mat on the floor, and there's going to be a coil on the underside of the vehicle as well. So when the car pulls over the mat on the floor, there's energy transferred from the mat to the vehicle, and that's kind of how wireless charging works. And many situations have been considered where opportunity charging can be done for buses, where they stop during, it's either a stop sign, or if you stop at a bus stop, you can do high power transfer, so you top off the battery, and such a way you can extend the range. So wireless power transfer has been there for a long time. I'll skip the equations and all those things in transformers. The main difference between this and the transformers we know is the core is not there, so it's a loosely coupled air-cored system, but we use resonant, and you might hear this word often, resonant wireless charging. So in this system, you have resonance and electromagnetic induction, which is going to help the transfer power. That's about the technical details I'll stick to. So in terms of the technology readiness level, SAE, Society for Automotive Engineers in USA, is working on a standard for wireless charging. And the standard deals with up to 20 kilowatt systems, and the production units are expected to come out early next year. So why high power wireless charging? If the standards are looking at up to 20 kilowatts, why are we looking at 100 kilowatts or 120 kilowatts? Because there's a big need for fast charging, and if we go to the dynamic charging case, as the car is going, if you want to transfer power, you want to transfer more power because you get more energy for a duration of time. So there are many reasons why we're looking at 120 kilowatt plus wireless charging. What are the main challenges? If we go to 100 kilowatts, what's the size of the coil? That's the main question that comes up, right? I mean, OEMs, the first thing they ask is what's the weight, what's the cost, and how big, what's the footprint? So we have to make the coil as small as possible, which goes on the vehicle. We have to make the electronics as small as possible that goes on the vehicle. Some of the key enabling technologies which is needed to make the coils in the system smaller are wide bandgap devices based power electronics, so that you can operate at higher frequency. If you operate at higher frequency, the passive components goes down, and silicon carbide based inverters, they can operate at a much higher temperature, so the heat sinking required goes down. So you can shrink the overall system, and this kind of shows the trend. If you go from 22 kilohertz switching frequency to 85 kilohertz switching frequency, you can shrink the size by almost half of the coil. There are other novel materials and technologies you can look at to reduce the size as well. And there's a lot of computational and FEA kind of work which is needed to do the electromagnetic fields. And of course, the other question we get often in US is what's going to happen to the cat or dog in the house if you're charging the car, right? So we have to look at the emissions and the safety. There's ICNIRP, which is the International Commission for Non-Ionizing Radiation Protection. And the systems that we are developing and the other OEMs and the tier ones that are developing are all compliant to the international safety standards. So it's as safe as your microwave, as long as you don't put your head inside the microwave. So I already talked about the wide bandgap based power electronics, and the power electronics itself, which is kind of the driving force for high power wireless charging. So this is the inverter which drives the wireless charging system, which is seen here. This was validated up to 120 kilowatts. This is a laboratory prototype yet. It's not integrated and demonstrated on a vehicle because it's in very early R&D, but that's ongoing work. The weight of the onboard electronics is like 4.6 kilograms for 120 kilowatts operation. That leads to like 26 kilowatts per kilogram. So that's really power dense. If there's any power electronics person here, we can discuss later. The size of the coil was around 800 millimeters by 700 millimeters, so it's kind of large, but it can go into a bus, and we're working on a lot of things to shrink the size, and I would say 30% reduction or 40% reduction of the coil size is definitely possible. The weight was 52 kilograms, which is kind of, some might say heavy, but again, we are pushing on that to reduce the weight as well, and we think we can bring it down to 25 or 30 kilograms for 120 kilowatt operation. These are the laboratory prototype coils, and it's not yet put on the vehicles, as I said, that's going on. And like one of the questions which keep coming up is like, where did you put it to test it, right? I mean, so there's not many vehicles which can take 120 kilowatt charging at this stage, so we had to use battery emulators, and we used grid emulators to supply the thing inside the laboratory as well. And the most important question we keep getting is, oh, wireless charging, it must not be efficient. Our system was 97% efficient from DC to the battery. So we just lost 3%. The input power was 124.5 kilowatts, and the output power was 120 kilowatts. So it's very efficient. This is the perfectly aligned case, but still overall the efficiency will definitely be more than 90%. So I would like to thank the US Department of Energy, Office of Energy Efficiency and Renewable Energy, and the Vehicle Technologies Office, which supported this work. And I think if you have any questions, we can take it offline, or feel free to send me an email. Thank you.
Thank you, Veda. We'll certainly give some time for question and answers later. Thanks for excellent presentation.